ethers, epoxides, and thioethers. In this chapter, we will learn how to name these compounds, and we will learn also about their methods of prep and their reactions. Ethers usually are compounds that have a functional group that is carbon, oxygen, carbon, and either of the two carbons can be primary, secondary, or tertiary, or even a methyl. Now, ether compounds can be actually symmetrical or unsymmetrical. What do we mean by that? What we mean by that is if we look at the first example right here, what do we have? We have an ethyl and ethyl. So that's a symmetrical ether compound. An unsymmetrical ether compound would be when you have two different alkyl groups. So in this case, you have a methyl and you have a phenyl. So that's a methyl phenyl ether. We will learn how those compounds are being named. Tetrahydrofuran is one of the important solvents actually used in organic chemistry. So ethers can also be cyclic, not necessarily just a straight chain compounds. When it comes to the hybridization around the oxygen, of course, because of the presence of the 4 electron groups, 2 lone pairs, and the 2 alkyl groups, that makes it an sp3 hybridized atom. It's a bent in terms of shape, but the bond angle, it's wider than a tetrahedral bond angle due to the fact that the atomic size of 2 carbon atoms, that pushes the bond angle to be a little wider than what it is the usual case. If you would have, for example, water, it will be less than 109.5. But if in this case, because of the alkyl group, that will make it actually a little more expanded bond angle due to the atomic size of those atoms. Usually, these bonds are polar, and the polarity comes from the difference in electronegativity. The electronegativity could reach about a 1 value. Boiling point. When we look at ethers versus alcohol versus alkanes, what we notice that the difference in their intermolecular forces contributes to their physical properties. So ethers kind of fall between the two main compounds, alkanes and alcohols. Alkanes usually form London dispersion forces, nonpolar compounds, therefore their boiling point will be the least among these 3 functionality. Alcohols, because of the fact that they form intermolecular forces that are very strong, hydrogen bonding, that makes them actually the highest in terms of boiling point or melting point. So ethers, compared to similar number of carbons, whether you have an alcohol or you have an alkane to compare it to, usually they are closer to the alkane than it is to the alcohol. And the reason behind that is due to the fact that they don't form hydrogen bonding. They are hydrogen bonding acceptors, but they are not, they cannot form hydrogen bonding with each other as ether compound. What do they form then? They form dipole-dipole intermolecular forces. And that's, of course, in terms of strength, it's weaker than hydrogen bonding, and that's what contributes to the lower boiling point of these compounds compared to alcohols. And you can see here clearly that if I would have an alcohol, for example, next to another alcohol, that will be basically both candidates will be alcohol, will be hydrogen bond acceptor and a hydrogen bond donor. But if I have an ether next to another ether, neither of the two are hydrogen bond acceptor or donor. So therefore, they cannot form hydrogen bonding. What can they form? Dipole-dipole intermolecular forces. And if I would have an ether in an alcohol, I would expect the solubility to actually increase compared to nonpolar compounds due to the fact that you have 2 candidates now that both of them are eligible to make hydrogen bonds. So that alcohol will be the hydrogen bond donor and the ether will be the hydrogen bond acceptor. This is an interesting table to extract some trends. So dimethyl ether, you can see here clearly that the boiling point is around -25 Celsius. Increasing the chain on either side, that will increase the boiling point. Now, having a branched alkyl compared to a straight chain alkyl, of course, the branched chain will have a lower boiling point due to the fact that lesser points of interaction. And that's what we usually see in alkanes versus branched alkanes. Branched alkanes you will have a lower boiling point compared to the corresponding straight chain alkanes. If I would have additional oxygen atoms, of course, I will be noticing that stronger dipole-dipole interaction, therefore a higher boiling point corresponding compared to a single oxygen-containing compound. Ethers, they can be used in several applications, one of which they can be used as solvents. So the fact that they can dissolve nonpolar and polar substances, and they can basically be unreactive towards strong bases because of the fact that they don't have an acidic hydrogen. That gives them basically the feature that they can be used as solvents. Add to that, the vapor pressure is very high. That make them really good candidates actually for sensitive reactions to moisture or oxygen. So that these ether compounds, they can be used as a medium to protect the reaction content, therefore the reaction can take place. Ether is an example of a polar A product solvent. And we've seen this example of solvents in the application of nucleophilic substitution type 2. And it's important to use such solvents due to the fact that when you have a nucleophile, that's a counter-cation and a counter-anion, these ether solvents, what they do, they form like a solvolysis cage. They solvate the cation. So you can see here clearly lithium iodide as an example. Lithium is being solvated. That frees up the iodide to make it even a better nucleophile. And that's why you see polar A product solvents are actually used in SN2 versus SN1, due to the fact that what you need for the SN1 is to actually do breaking the carbon X bond. You can't use ether for that purpose. You would have to use polar product solvents. And that's the difference between the two pathways when it comes to a solvent effect. And as I mentioned, in Grignard reactions, ethers usually what's been used. It's not the only type of solvents that we can use, but most reactions that are Grignard reactions usually utilize ether as a solvent. So they stabilize the reagent and they help them keep it in solution. So that's important actually for the reaction to proceed. And not only that, if I look at the BH3, which is borane, the fact that there is a Lewis acid Lewis base reaction between the two, BH3 and an ether solvent, that stabilizes the BH3 for longer. And that's what we usually see when we bring a bottle of BH3. We notice that it's actually a complex, BH3 THF. THF is just being a solvent here. It has nothing to do with the reaction, but it has to do with basically stabilizing the BH3 to give it a longer half-life. Crown ethers are being also used in nucleophilic substitution. So we've seen those complexes previously, and we noticed that each crown ether type is specific for a certain metal. So for example, 12 crown 4 is for lithium. These help solvate the cation, and that will free up the anion to become a stronger nucleophile. See the 15.5, for example, for sodium, 18.6 for potassium. So what's good about these complexes that if I don't end up using a polar A product solvent, like an ether type solvent, for example, I can use a non-polar organic solvent and I will throw in a crown ether that will help in doing solvolysis of the anion, of the cation, to free up the anion in those nucleophilic substitution reactions. Naming ethers can be following a common name system or an IUPAC system. The common name depends on the ether. Is it a symmetrical compound or is it an unsymmetrical compound? If it's a symmetrical compound, all what you have to say is dialkyl ether, or you could say alkyl ether. So as an example, you have CH3, CH2, O, CH2, CH3. That's a diethyl ether, or you could just say ethyl ether. But if it's an unsymmetrical ether compound, then you're going to have to basically recognize each alkyl group and list them alphabetically. So the correct name here would be TBME, terburyl methyl ether, TBME. That's the abbreviation actually for this type of solvent. So that's how we usually name ethers following common system. Now, the IUPAC system treats the ether as an alkoxy group, as a substituent. So the very first rule when it comes to naming an ether compound following IUPAC set of rules is to find the longest chain of carbons. So if I look at the compound on the left, what do I have? I have 1, 2, 3. That's the longest chain of carbons, which is propane. And what do I have on it? I have a methyl and I have a methoxy. So alphabetically, I will list obviously the methyl first. So 2-methyl, 2-methoxy, propane. Here's another example. So we have a cyclohexane. That's the parent name, and I have a methoxy group that's sitting on it. So that's how we name ethers following IUPAC set of rules. Here's some heterocycles or cyclic ethers. So we've seen this previously when we made epoxides from alkenes. That's an oxirane. Here's an oxetane. Here's an oxalones or THF. Here's an oxanes with a 5-member ring with a 6-member ring with an oxygen inserted. You have the pyrane, you have the furan. These are very important actually to keep in mind what these structures are, because most of them, they are used as solvents, such as THF and dioxane. So dioxane, 1,4-dioxane, that's another example of a polar A-product solvent. Now, when it comes to naming epoxide, it's a little different. So there is the system that we could just go back to the corresponding alkene, name the alkene, and then insert the word oxide after. So here's a cyclohexene. You make an epoxide out of it. That's a cyclohexene oxide. What's more actually common to use following IUPAC is to treat this group as an epoxy group. So previously, the straight chain ethers, we treated the RO as an alkoxy. This time we would treat it as an epoxy. Numbering will start from the epoxy group, giving 1 and 2 for the epoxy carbons. So that's what you have here. 1, 2, 3, 4. So I have a 4-methyl and I have a 1,2 epoxy. Now, alphabetically, obviously you will start with the epoxy. So it's a trans due to the fact that you have 2 different faces where these 2 groups are. So you have a trans, 1,2 epoxy, 4-methyl cyclohexane. Same thing here. What do I have? I have an epoxy group that is sitting on carbon number 2 and 3, and I have the longest chain of carbons that is 6. So 1, 2, 3. So 2, 3 epoxy, 4 methoxy, and so on. So which one would we list first? Obviously the epoxy. Now the 2 groups are on the same phase, so that's a cis, 2, 3, 2, 3 epoxy, 4 methoxy hexane. So that's how we name epoxides following IUPAC set of rules. The ether in a straight chain, that's an alkoxy. In the epoxides will be named as epoxy substituent. Here's some more examples. So this is a 1,2 epoxy ethane. That's the IUPAC. For a common name, that's an oxirane. This is an oxirane. That's the smallest cyclic ether you can have. Here's another structure. So we have 1, 2, 3, 4, 5, 6. So that's a hexane. I have a substituent on carbon number 2, and I have a substituent on carbon number 4. So that's a 4-ethyl, and that's a 2-methyl. And you have the 3 and 4 carbons. You have an epoxy group sitting. So I have a epoxy, and I have an ethyl, and I have a methyl. So obviously the epoxy would be first. So that's why 3, 4 epoxy, 4-methyl, 2-methyl hexane. Here's another example. So we have 1, 2. So that's a 1, 2 epoxy, 1 methoxy propane. So that's a trans. And that's why you have in front of it, that's trans, 1, 2 epoxy, 1 methoxy propane. So that's important to keep in mind how we name ethers versus epoxides. The most important method of prep of ethers is the Williamson ether synthesis. We've seen this reaction previously. How do we generate the alkoxide? We take an alcohol and we treat it with sodium or potassium or sodium hydride. And what do we get out of that? We get the alkoxide plus H2 gas. The alkoxide, if I react it with a methyl X or a primary X, I get the dialkyl ether, or whatever the two R groups are. So it's an SN2 pathway, and it's important that I use primary or a methyl tosylate or halide. Why not secondary or tertiary? Well, secondary halide or tertiary halide will go through elimination, E2 rather than SN2. So you end up making an alkene rather than an ether compound. So you could see here some examples of the Williamson ether synthesis. So you have a cyclohexanol treated with sodium, that's going to give me the alkoxide, and that alkoxide will attack the primary tosylate. So you can end up making an SN2 pathway, SN2 outcome that's a cyclohexyl ethyl ether. Cyclohexyl ethyl ether. Or the IUPAC name would be ethoxycyclohexane. Here's another alcohol compound that treated with sodium hydride that's going to give you the alkoxide attacking methyl that will give me the 2-methoxy-3,3-dimethyl pentane. So Williamson ether synthesis usually has really good outcome, and as long as we use a methyl or a primary halide or tosylate. Phenol pK is about 10 compared to an alcohol. That's around 16. So phenol will be easier actually to generate a phenoxide due to the fact that the base, the conjugate base, is more stabilized. So if I treat a phenol compound with an NaOH, that's going to give me the phenoxide. Phenoxide will attack the primary or methyl tosylate halide. That's going to give me basically the SN2 outcome as well. This is important. Phenyl halides or tosylates cannot be used in this synthesis method. As a candidate, I cannot have in the SN2 pathway a phenyl halide or a phenyl tosylate due to the fact that the sp2 carbon X bond, it's a very strong bond. It's not that easy to break. Therefore, these are usually unreactive in SN2 pathways. So here's a question. So the interest is to make terbutyl propyl ether, which is this compound right here, terbutyl methyl ether. The question is, will this pathway work? So starting with a sodium propoxide, so taking this and O minus, and that will be basically coming from the alcohol. You generate the alkoxide from the alcohol using sodium or lithium or potassium or sodium hydride, and attacking that tertiary alkyl bromide, that's not going to give me an SN2 pathway. In fact, we said this previously, methoxide, even if I use it with a tertiary alkyl halide, that's going to give me an E2 pathway, E2 outcome. So that's going to give me an alkene rather. So if I take that sodium propoxide and treat a tertiary or a secondary, what's going to end up happening, I'm going to end up having an E2 pathway. So here's what's happening. So you have a propoxide is going to look for a hydrogen to abstract due to the fact it's a tertiary halide, and that's hydrogen is going to come from the alpha carbon that's adjacent to CX, and that's going to give me the alkene at the end. So it's going to be useless pathway to end up making a compound that is not the desired compound. How would I make this then? How would I make this terbutyl propyl ether? I need to think of which of the two alkyl groups would be a candidate for a methyl X or a primary X. So clearly, it's going to have to be the propyl. So propyl halide or propyl tosylate plus the alkoxide. So you're going to have to break this bond right here. This will be your alkoxide candidate, and this will be the propyl X, which is going to be the tosylate or the halide. That will be the second candidate in the Williamson ether synthesis. So the proper way to do it is to start with terbutanol, treat it with sodium, potassium, or sodium hydride. That will give you the sodium terbutoxide. Attack a propyl bromide that then will go through SN2 pathway to give you the desired product. So that's important to keep in mind. How we do synthesis with the best efficient method to do so. You cannot claim that your synthetic route that you propose is inefficient if your outcome or the intermediates that you are getting out of that synthesis are actually minor compounds. They have to be major compounds. So the second method that we can make ethers out of is the alkoxymercuration demercuration. We've seen the oxymercuration demercuration of alkenes, how it actually forms an alcohol. What we do here is, rather than using mercury 2-acetate water followed by a step sodium borohydride, we use mercury 2-acetate alcohol to form the mercurinium ion. And this mercurinium intermediate then will be treated with sodium borohydride to give you the alkoxy group that's going to make this compound an ether compound. So that's the difference between oxymercuration and alkoxymercuration. The alkoxymercuration will use alcohol instead of water, and the oxygen will be the one that's going to attack the more substituted carbon on that mercurinium ion to end up making the ether at the end. Another way that is considered to be an industrial approach, not a lab setting approach, is to make ethers out of bimolecular condensation of alcohols. So if you take two alcohol compounds, obviously the two will be the same, and treat it with acid and heat, what you end up making an ether compound. So the process is basically you protonate one of them with the acid, and then the other alcohol will attack that activated protonated oxygen to kick it off as water molecule, and that will end up making the ether compound. Now, there are drawbacks for this. What is it? One, it requires a primary alcohol. You cannot do secondary or tertiary alcohol due to the fact that it's going to give you elimination outcome. The second drawback is the high temperature that is required. The problem with it, that some temperature cutoff will not actually produce the ether compound, will probably produce the alkene instead. So here's an example. You have a propyl alcohol reacting with itself in presence of sulfuric acid in 140 Celsius, you end up making the dipropyl ether or the propyl ether. But if you take that isopropyl alcohol as an example, 140 Celsius sulfuric acid, that's going to push it to give you the elimination outcome instead. So that's why this method is considered to be an industrial method, not a lab setting method. Reactions of ethers. The most important reaction of ethers is the reaction with hydrohalic acids. So HBr or HI. HI actually much more reactive compared to HBr. So how do these reagents react with an ether? Well, it's going to basically cleave the oxygen-carbon bond, but in order for it to go through that cleavage, it has to go through the first step, that is protonation. So the very first step, because ethers are usually a very bad leaving group. So you can't just react with a nucleophile and assume the CO bond will just break on its own. What's going to happen, the very first step will be protonation of the oxygen using HX. So oxygen will attack the hydrogen, will kick off the halide, so that's going to give you the oxonium ion. This is now a good leaving group. The ROH is a good leaving group. So what's going to happen next? Br minus or I minus will attack R. That carbon, it's going to be attacked through an SN2 pathway, and it's going to kick off the alcohol. What's going to happen next? This alcohol will go through the same process again. Will get protonated, and once it gets protonated, it's going to be attacked by the halide to give you the alkyl halide. So you end up always making the alkyl halide from both sides of that ether compound. When will this not go on to the second alkyl group? If I have a phenyl ethyl ether as an example, or ethyl phenyl ether, reacting with HBr, look what's happening. Oxygen attacks the hydrogen, it's going to protonate, so it's going to give you a reactive ether compound now. Halide will attack the alkyl, not the phenyl. Why? Because the phenyl group, as we mentioned previously, they are very bad candidate for substitution. So that's why the halide will attack the primary carbon, and that's going to give you basically an ethyl bromide plus phenol, and the phenol will not be further reaction with an hydrohalic acid. So it will stop at this point. Auto-oxidation of ethers, it's an aspect that we have to pay attention to when it comes to storing ether compounds. In the presence of atmospheric oxygen, ether usually oxidizes to hydroperoxide and dialkyl peroxide, and we'll see what these compounds are. Both are highly explosive, and that's why that we can't store them for too long. That's why we are required actually by the agency to label these bottles once we receive them, like diethyl ether as an example, or THF. We have to label the bottle the moment we get it, and we usually are recommend to dispose them within 6 months to 1 year. Don't distill to dryness, because that will actually push the auto oxidation to take place. And we usually have to store them in full bottles with tight caps, so not allow any oxygen being trapped on top of those liquids. So here's the auto oxidation reaction. So you have as an example, you have an ether compound. Depending on the substitution of the alkyl group, it could be a very slow process. So it takes longer for a substituted ether than a straight chain ether. So when you do that, when oxygen reacts with ether compound, what's going to happen? One of the two, if not both. The hydroperoxide, so you end up basically having that carbon that's attached to an oxygen to be the hydroperoxy moiety, or an insertion of an oxygen into that ether compound to become a peroxide. So these two are actually considered highly explosive, and that's the source of fire. If we store the bottle of ether for too long and we open it in presence of oxygen, that's actually going to be a source of fire. So that's important to keep in mind. Here's an example of a branched alkyl ether. So we have oxygen reacting with it. So that's going to give you basically the hydroperoxide plus the diisopropyl peroxide. Next, we will be learning about thioethers, and we will look at epoxides, how we name them, how we prepare them, and their reactions to generate useful compounds.